Hello and welcome to Unboxed, the SRF Podcast. I'm your host, Nick Bussey, Multimedia Manager here at SRF Consulting Group. And today we're going to talk about a groundbreaking study that SRF recently did for the Minnesota Department of Transportation, looking at how lane keeping systems in modern vehicles perform in work zones. And the results are pretty interesting. To discuss this topic, we have three of our in-house experts who worked on the project. First to my left, we have Eric Minge. Eric is a director in the Intelligent Transportation Systems Connected Automated Vehicles Group, also known as ITS CAV, here at SRF. Next, we have Uthej Vatapalli, an engineer in our ITS group. His work encompasses areas such as construction materials, transport law, and autonomous vehicles. And then last but not least, we have John Jakels. John is project manager in our ITS group. He's a registered professional engineer in the state of Minnesota and a professional traffic operations engineer. He retired from MnDOT in January 2014 after more than 39 years of state service. Gentlemen, welcome to the podcast. Thank you for being here for this inaugural episode of Unboxed. And I want to jump right into this study. So obviously work zone safety is an urgent issue. Just this fall, we had 2 construction workers killed in the course of 2 days in work zones here in the Twin Cities. So I'm not sure who's the best person to take this question, but if somebody wants to just maybe start with an overview of what was the origin of this project and what was MnDOT looking to find out?
Yeah, I'll start answering that one, and I'll throw out there that modern vehicles have a lot of different technologies on them, and advanced driving systems called ADAS, Advanced Driver Assist Systems, offer a range of safety improvements on vehicles such as adaptive cruise control, emergency braking, and lane keeping systems. And that's what we're looking at here with this study. And those are vehicles that have technologies that center the vehicle in a lane or warn a vehicle when it's going to depart from a lane, also called lane departure warning. And all of those are designed to work in typical roadway settings. And this study was seen as a way to assess what happens in work zones with different pavement markings. And MnDOT saw that as a need and initiated this study. So we were fortunate with this project to have great leadership from MnDOT. I want to mention here the project manager, Adam Wellner, that got us started and headed off with this project. And then Scott Meyer came in and wrapped up in a project manager role. Also participating was Michelle Moser. She's MnDOT's work zone engineer and provided a lot of guidance on work zone practices. And also Dan Rowe participated in the project and assisted from MnDOT as well. We also had a couple of project partners. ViaSight provided the in-vehicle technology that was used to assess the pavement marking quality from an objective standpoint with their standalone system. Phil Magny was the lead of that team. And then we also had a traffic control contractor, Safety Signs, led by Reed Ledley, and they set up these simulated work zones at MnDOT. They provided the drums and the cones, and they removed the pavement markings and such, and then restored everything back to the previous condition when the project was over. So I just want to acknowledge those aspects of our team as well.
These systems are all a little bit different, right? So you have these different auto manufacturers, and they're all sort of developing their own technologies. And so it was important to sort of get kind of a cross-section of different vehicles, right? Well, first of all, what are the variety of things that these systems would encounter in a work zone environment that could potentially be confusing? So we're talking about traffic cones and drums, but also other forms of delineations in work zones, right?
Yeah, and I can answer that, Nick. It's I think that in work zones, we're not able to always provide all the pavement markings and all the traffic controls that we have on the regular roadways that these systems rely on. So MnDOT really wanted to know what impact does that have, and what can they do and afford to be able to do to address that, or at least know that the designers and the field operations people know how these systems are going to react in their work zones. And I think the challenge of this study was to find what is typical in work zones. And we started off with a test section at the MnROAD research segment that we could test different things outside of traffic, and then moved into the real world work zones to see how does it really apply to things that are out there in the real world. And we didn't set up those real world. We just took projects that were already out there.
Okay. You mentioned MnROAD. Let's talk about that for a second. For people who don't know what that is, MnDOT has a very unique pavement testing facility, kind of in the northwest of the Twin Cities here. And why was that facility chosen for the first part of the study?
It's a typical roadway section. There's no traffic, so we could do whatever we wanted to do out there as far as setting up scenarios for the test without any worry about liability and safety and things out there. And then when we were out there doing that initial testing, just to see how these systems would perform in those areas, we could adjust and change that at that time.
Another advantage of MnROAD is that it's a circular looped test track, so it allows test vehicles to drive, follow around, loop, and do multiple runs, and kind of get that repeatability by multiple data points.
Yeah, but from a research standpoint of view, this offers a more controlled way of testing. You can pick a particular feature of the work zone that you want to test your system against, which is not something that you would be able to encounter in real world because of how many different setups of work zones come together in real life. So if you want to test the cause and effect relationship between a particular work zone characteristic against how these lane keep systems perform, MnROAD facility offers you that controlled setting.
Sure. And I'll mention too, we did make a short video about the first phase of this project. We'll put a link to it in the description for people who want to check it out, who just want to get a glimpse of MnROAD. It's a very interesting facility. And then maybe let's talk about the types of simulated work zones that were set up at MnROAD. Can you give like an overview or a sense of the variety? Because the way these systems work, these lane keeping systems, is they sort of look for visual cues, which is normally the stripes painted on the side of the road, right? So they try and stay in between the lines, and that's the idea, is that they help drivers stay between the lines. And when you go into a work zone, you could have a taper of cones, or you could have pavement that was removed or altered in some way. Can you just kind of give a sense of what some of those things look like?
Well, Nick, there were 15 different scenarios we did, and the advantage at MnROAD is we could take pavement markings off in different methods. We use grinding and water blasting and covering with black tape, and see how those three work together and how they perform. We could provide different pavement markings like temporary raised pavement markers. We could use different channelizers, cones, which are smaller, and drums, which are larger for the vehicles. And we could adjust those on the fly, so to speak, like Eric talked about, be able to make adjustments to that. In fact, they did that at MnROAD to test some alternatives that we didn't have on that test track, based on what they found during that controlled segment that Uthig was talking about. That you can make those changes and do adjustments for that. So pretty much everything you're going to encounter in real world work zones, but it was controlled.
Okay. And then how did we collect the data, or what kind of data did we even collect? How do you go about setting up a test for something like this, where you've got different vehicles, different technologies? What kind of technology was used in the actual test environment?
So all the processing was done over video and video data that we collected, and 3 different views were important for us. One was what are we looking at on the road when we're driving? And then 2, what is the vehicle system indicating on the dashboard? So we would have a camera facing the vehicle dashboard that would give us that information, whether the lane keep system is turned on or turned off. Typically, all the vehicle dashboards give an indication when they're on and off. So we wanted to collect that. And then the third is where our partner ViaSight comes into picture. They have their ViaSight analytics that is a good proxy for how these systems are working. What are they seeing in that particular frame? This is also video format, but that is what they're looking for and serving as a proxy for the vehicle. And the reason we needed that proxy is because all these vehicles are sort of a black box. You don't really know how they are working, what they're looking at, how far on the road they're looking at, are they immediate frame. So we needed a good way to understand and look into that black box in our ViaSight analytics. So in summary, there were 3 cameras, one looking on the road, one looking at the vehicle dashboard, and then one collecting analytics to evaluate the different to assign performance scores to the roadway settings that we were looking at.
Okay. Well, let's talk.
And I'll maybe expand on that a little bit. I think that black box piece is really important to touch on again, because when we look at a vehicle, we rented vehicles for the study, and they only indicate whether the system is engaged in providing lane keeping technology at a given time or whether it's disengaged. And so it's a binary status of that system, and we can only identify when it disengages and then re-engages. And that provides a little bit more of a limited assessment of the quality of what's out there for work zones.
Got it. Let's talk about some of the results of that first part of the testing at MnROAD. And maybe just to give a little spoiler alert, my understanding is that the results were a little bit different from MnROAD versus the real world testing, but let's just start with what do we learn from MnROAD? How did the systems perform generally? Are they generally pretty good?
So yes, in MnROAD, the settings, like day one, we had no complications in terms of how the work zones were set up. They were all linear work zones, and the vehicles did pretty well. But the only thing that we wanted them to perform, and they did perform well too, is the removal methods. Especially what we've learned was water blasting. So there are 3 types of pavement marking removal methods. One is putting a blackout tape. Second is removing them using a grinding machine. And then third, you water blast it. So of the 3, what we found out is water blasting was the most effective method, because whether you're using blackout tape or grounding out the pavement marking, the vehicles would inconsistently pick up that. And that's not the intended purpose of why we are removing the markings. So that was one major set of learnings. And then the other one is the fact that cones and barrels do not get detected as channelizers or as lane separators. Now, the Tesla vehicle, the Tesla Model Y that we tested, that would pick up the fact that there is an object there, but it wasn't necessarily using that to make decisions, especially when we're talking about on autopilot.
Right. And so that actually brings up something, and maybe we should take a step back. So the whole idea with lane keeping systems is they help the driver stay between the lines, but ideally drivers are paying attention. And so they should be able to see there's a work zone coming. Oh, I should change lanes. But I think the idea with the study is, we can't always depend on drivers to understand the technology in their vehicles, be sure they're paying attention. So MnDOT wanted to know what happens if it's just the lane keeping system looking at the road, right? Is that kind of...
And I think, Dick, you touched on that. It's just, what is the risk?
Yeah.
With how are these going to perform differently than drivers that are using their own systems, their eyes and controlling that vehicle?
Right.
How are these going to react differently? And we did see differences more so in the real world part, what we can talk about in a minute.
Yeah.
But at MnROAD, they all, like Uthik said, they all responded very similar. And I think one thing that we haven't touched on yet is at MnROAD, we have a commercial vehicle there. We had a semi. One of the questions that MnDOT had is, do semis react differently? When you're out there on the side of the highway working, okay, cars are scary enough, all right? But these heavy 80,000-pound vehicles are even more dangerous for workers out there. And everyone's concerned about that. How did they respond? And I think, you could speak to that, but we didn't see a difference. The angles, the videos that they're done this, the angles on the trucks are way different, but they reacted very well during the MnROAD test.
I actually need to correct that. We did see a difference when there was a difference in the mounting height of the camera. But again, I would like to emphasize that this is based on our partner ViaSight analytics and watching observing the differences by having their analytics be present at different heights. So because a commercial vehicle would be way taller than our regular passenger vehicles, we did note that it was more consistent in picking up both blackout tape and ground out methods of pavement marking removals.
Okay.
So that this is an indication that the height matters. But that being said, it comes down to the performance of the lane keep system. It did not perform as well as the other vehicles, partly because it was a level 1 system, which is it helps you with lane departure, but not necessarily keep the lane well for you.
Okay.
The lane centering piece isn't really emphasized in that kind of system.
Yep. That's one of the challenges of working on these vehicles that are coming just going and renting out vehicles, is you do not have too much control over the systems. We were very fortunate to find the vehicles that do have those level 2 systems where they're lane centering for you.
Right.
But that's not a guarantee that can always happen.
So what did we have there? So I remember, because I went out and visited the team one day when you were doing your research. So I remember seeing a Toyota Camry, a Hyundai, was it
Palisade?
Okay. And then
A Tesla Model Y.
Tesla Model Y.
A Ford Bronco.
Ford Bronco? Okay.
Yeah. And these were all 2025 models used during the real world testing, which is for MnROAD, we had sort of similar mix. The Tesla Model Y, the same Tesla Model Y we used for real life work zone. A 2024 Toyota Camry and a 2024 Hyundai Elantra. And then the last vehicle, actually for fun, we did one more vehicle extra, which was the Ford F-150, but that wasn't part of this test. That was more of like, we want to have fun with it.
Sure. Okay. Well, let's talk about the real world testing then. So once we took these out in the real world, which I got the chance to observe a little piece of that too. What were some of the challenges there, first of all? I imagine there's all kinds of challenges in real world versus a controlled environment like MnROAD. Who wants to take that one?
I think the major challenge is finding the projects that had the pavement markings or not pavement markings and channelization that we were looking for the study, because we couldn't adjust that. The real world is you get what you get. We were fortunate enough to find those, across the state. So it was good to do that, but it still had limitations. So, if you look at the report, you're going to see that some considerations for future looking at that, because there were things that weren't in the real world projects that we looked at, but they were well represented, with pavement markings that were met the standards all the time, and others that didn't quite do that, and not being critical of that, but it's just what you find out there. So we did have a good range of what we found on those work zones.
And the testing went fairly smoothly in terms of the drivers all meeting ahead of time and getting familiar with the technology in their vehicles, how to start the recording of the camera systems that were on board, and then meeting up at a reference place and getting organized and beginning a run as kind of a group staying together and coordinating activities. So there's relatively consistent vehicle speeds that were traveled and how the lane keeping system was allowed to operate on its own as much as possible without driver intervention. So that part went fairly smoothly, and we were able to capture the runs we needed. The weather cooperated. Things fell into place that way. It was more the results analysis that it was hard to tease out the real findings. And that's something Udaj had mentioned here earlier, was there's just a lot of variables, and isolating what the intended variable was, say, for example, a different type of lane marking than would normally be used. It was hard to isolate that variable and point to a specific finding from that.
Yeah. Like if in one, let's say, frame that you're looking at in the video, you can find drums and cones and no pavement markings. But then on top of that, you will also have a bituminous pavement marking, or like a bituminous pavement and a concrete pavement, which in the layman's language, that is basically a white pavement and a black pavement. And now, since there is contrast present, along with the other channelizers, the drums and the cones. Now we don't know why the lane keep system chose not to work, or if it veered off in a different direction. So it's just real world was more complex. It wasn't as clean as you would like it to be. But that being said, it did offer more scenarios than we could have planned for at MnROAD, and that was good in itself.
Mm-hmm. We do have some footage of the tests both at MnROAD and in the real world, so I thought maybe I would just pull that up and we could kind of talk through, and I'll talk people through it for the people who are just listening to the audio. Let's start with MnROAD. So we're looking at basically a simulated lane closure here. We've got a bunch of drums closing a lane, and we're going to see the vehicles coming toward the drums. And then if somebody could kind of describe what's happening in the vehicles, maybe, or maybe what the driver, what's happening from their perspective as these tests are happening. So hit play here.
Yeah, I can throw in a thought here. The vehicles are approaching this line of drums and are not making any action at all. They're headed right towards that line, and the driver has to take control of the vehicle, override the lane keeping system to avoid striking a drone. And then this video is of a different vehicle. That looks like the Tesla, and that one did fine looking at that line of drums. I believe that one was in full self-driving mode and was able to do that. But here we have another one that is headed right for a barrel, and then the driver takes control. So, I think this is an important point to make here is we've got these lane keeping systems, and if you're relying on them, maybe you're distracted or, not fully engaged in the driving process because you've got a vehicle that's doing so well in most conditions, and then you come upon a work zone, that's when you could run into trouble. You might head right into a work zone and not realize that the system has disengaged and is not properly functioning.
I have to say, as somebody who wasn't in the car when this was happening, this looks a little hair-raising, honestly. Like you're heading straight for these drums. I mean, these ones are at fairly low speeds, but still, like you have to sort of play a game of, letting the system do its thing and find out how close it's going to get, but make sure you don't crash into the drums. That must have been interesting.
And I should correct myself. The system did not disengage. It stayed pointing straight ahead and felt like it was doing what it was supposed to do. So I think that was a major finding that we came away with.
Interesting.
Yeah, but it does take a certain level of bad boys to run this test, and we got the right kind.
And we did hit a drum with a side view mirror on one of our passes, so we let it get close before intervening.
Yep. Yeah. Okay. Well, so here let's look at the real world environment. So this is actually drone footage of a work zone that I'm very familiar with because I live close by it. But this would be what? This would be the 610.
Eastbound 94 goes to eastbound 610.
Got it. Okay. So let's take a look at this. This was kind of a challenge to capture, I remember. But so the obvious difference here is you're on the road with other vehicles too. So that's like another wrinkle in this.
Yeah. And then random persons like that will just pop into your study.
Yeah. So how did that sort of complicate the data collection at all?
Fortunately, we chose timings of the day where we wouldn't be encountering a lot of this. 610 is just ridiculously busy compared to Hinckley, where we tested, Austin, where we tested, Princeton, where we tested, especially time of day that we tested.
Okay.
Also, it doesn't matter too much who is in front of us, as long as we have enough spacing between them and ourselves for our vehicles to do what we want them to do.
Okay. So what did we learn in the real world testing then? Anything different from the MnROAD findings? So
I'll start off with one interesting one, which is to do with yellow pavement marking. So I was driving a Ford Bronco 2025, and it would not pick up yellow pavement marking at all. It would straight away deviate from the lane if yellow pavement marking was present. So the joke is the most American car in our test sample cannot detect yellow pavement marking, which is apparently only used in America for lane markings.
That is interesting.
So yeah, that's a fun one. And but then there are other stuff like when there are extended dotted lines missing at transitions, like when when there is an exit present on your throughway, or there's an exit or an entry, and if you don't have extended dotted lines, then the vehicle gets confused which path to take, and generally tends to want to be on the right, and that means it'll take the exit, and you don't want that to be happening.
Right. Okay. So, I mean, we talked a little bit about some of the findings in terms of the different reactions of the systems to different work zones, but like big picture, what did we learn from this study? Like the big takeaways.
I think the high level learning is that all these systems work different, and they're all video based, for lane keeping and whatever system that is, and they're all different, and they're all going to be changing. So this is a snapshot in time for that. And I think what you saw in that video from 610 is that when there's conflicting markings, you don't know what line that system's going to follow. Like Luthig brought up, that the one didn't pick up the yellow line. So it would be following the broken white lines, which actually were conflicting markings that, really should not have been there, if you want to, not to be critical, but it caused problems with this. And I think for what I learned is, if we're talking about the safety of the workers, we have to give information to the workers that these systems don't react like we think they're going to react. And so you don't want to be in that area, in the transition areas. What we found at MnROAD at the beginning was in the tangent areas, they all responded just fine. And they all work just fine. But in those transition areas, the lane closures, and right at the end of that lane closure, that's where that risk area is. You don't want to be in that area if you don't have to be in that area, and make sure that you are paying attention to that as a worker. That's what I took away from that. Because we're not going to change what we're doing out there. We can't afford to do that. On shorter term work zones, you're going to have conflicting markings all the time. And so what should you do to know about that? Mm-hmm. So that's what I took away from it at a high level with this project.
Yeah, and I think a big takeaway for me was realizing how these vehicles all function a little bit differently, and they all have their proprietary systems, and they're not really looking at all the edge cases that are out there. And work zones present an edge case that I would say are not adequately researched and developed into how those systems operate. There's an understanding or expectation that drivers will take over control of a vehicle when they enter a work zone, and that became very apparent in our study. Is that the current systems are not really set up for that. I will give one footnote to that. Is we did test the Tesla in two different driving modes. One was kind of the basic driver assist package, which they call Autopilot, and Autopilot would have some of the same struggles as the other vehicles we tested, but there's also a full self-driving mode that Tesla offers, and our test vehicle was used in that mode as well, and that did very well in work zones and did not encounter any challenges with the various scenarios that we were presented with. So as we look towards the future and where vehicle technology can take us, if fully autonomous is implemented and becomes more widespread and is at the level that we witnessed here in 2025 in our study, then that holds good promise for improved driving safety.
Yep. But to summarize, what we've learned is pavement markings. It all comes down to pavement markings as we are looking at this current snapshot of technology and time.
That's what they're looking for.
Yep. That's what the vehicles are looking for. And I know we've spent a lot of time talking about the vehicles here, but the whole goal of the study is, what do we do with this information about vehicles, and how do we configure our work zones and present that information to the work zone designers to make sure that they have all the latest information to do what they want to do with this, information.
Is there so what happens next? Are they going to do more research into this area, or are they going to incorporate these findings, I imagine, into their kind of traffic operations design?
I would say from traffic operations and traffic design that we're going to be offering considerations to the designer. going to be offering considerations to the field personnel. You know, we can't necessarily change everything that we do, but here's the considerations that Uthik talks about the dotted lines. You know, those are on a longer term project are relatively affordable and relatively easy to do. So it's a consideration. But in other areas, when we've got black and white pavements that are split and the cars track either on the markings or the pavement color challenge, be aware of that, but there's really nothing you can do about that and be affordable and get the project built. So taking that forward and then, looking to the future is to continue to look at this as these systems evolve and are improving, going all the way to the self-driving mode, eventually, that's going to change over time. So this is a snapshot in time for us right now. So it's continual learning.
Yep. Yeah, I think we came away with several opportunities to kind of take this further. And what John just referred to is a big one. Repeat this study in a couple of years and see what the next crop of vehicle technologies can provide. And there'll maybe be other adjustments or considerations that roadway designers would want to take at that time, or maybe realize that a problem that we're seeing now has been resolved. So it's a changing landscape.
Yeah.
And then something we didn't touch on, and that is consider public education. People that drive these systems don't necessarily know how they work. They don't necessarily know how to disengage them or anything. And they become reliant on these systems, just like all of us do that we work for. And knowing that when you get to a work zone, you're going to have some issues that you need to be aware of. So it's a public education piece that's, a little different than the engineering side of the world. But I think that would really help, if you have these systems, here's what you can expect to see and get some information out there.
And for the folks who do go look at the vehicle manuals and the vehicle owner manual, the vehicle owner manual will list off 15 different reasons why your vehicle system will disengage. Which one are you to know? And of them, I don't think I can say with reasonable confidence there's not an explicit mention of like what the findings that we have here. Where cones and barrels are not going to be detected as lane separators. So this is like this increased educational piece for the our everyday drivers, and which includes ourselves. And for the work zone designers, one of the reasons we are not saying, hey, change everything is because 7 years ago, if you see that, there's no such technology. Now we are at a point where these are navigating your cookie cutter scenarios pretty easily. But then 4 years down the line, we don't know how that is going to look. And now you've overhauled and made so many design changes and now you got to adapt again. So it's like, let's look at how these systems evolve and if they address the problems of today, or if they plateau and do not evolve, and now it's time to make changes. So yeah. John jokes about this that I say the researcher answer is we need more research.
Yeah. Well, it certainly seems like a challenge. I mean, these technologies are evolving so quickly, but I think it's, to me as a driver, it's reassuring to know that MnDOT is taking a look at this and that there's some information now that they can look at and incorporate into their planning. I did want to ask just really briefly about the work of the ITS group at SRF generally and how this sort of fits into your portfolio of things that you do. Is this a typical project for your team, or is this a little bit unique?
Yeah, I guess I'll take a shot at that. In some ways, this is not unique because the application of technology to transportation takes all forms. And the work we do in our ITS section is very diverse. And some of it's traditional planning and design of roadway infrastructure deployment. But we also take a look at vehicle technologies, roadside technologies, and all the factors and impacts they have in a real world setting. So whether it's winter maintenance or intersection conflict warning for rural intersections, there's lots of kind of extended fields that get touched on, and this fits within the umbrella of that general work.
Yeah, hence the title is ITS/CAV. is because the ITS half is all the traditional design of implementing traffic technology devices and fiber connections or whatever connections is required. But then the exploratory and looking down more into the future aspects and researching about those latest and greatest technologies, that's where the CAV half comes into picture.
Great.
And I think, Nick, along with that is that we have the ability to do some research. We have the ability to know what the traditional things and what's commercially available out there and address real world problems, where the typical signing and pavement markings and things don't really address the issue of highway safety and mobility. We have the opportunity to look at these types of systems and say, how can we improve that? And how can we get after these fatal and injury crashes that are occurring out there, where traditional systems aren't as effective as the active ITS systems.
One other area of potential future research is to go back and address some of the challenges we had in live work zones, where there were so many variables and things happening at once that we couldn't really pull out what was the effect of one particular lane marking consideration that we were trying to explore. So doing more of that testing in a controlled environment like MnROAD, where we can simulate and control for more variables, would help us understand with more detailed insight into the impacts of what was happening.
Yep, that gives us the more quantitative answers to things, so that it's not just qualitative answers.
Great. Well, this seems like a pretty good place to end. Really interesting topic, interesting research. Does anyone have any final thoughts?
We're excited to share this project's finding here on the Unboxed podcast. I think it's a great application for some of the innovative work that's being done. So glad to be a part.
Great. Well, thank you so much for being here. And for those who are listening, we'll drop a link to the video that we reference in the description, and any other information or links that we reference in the show you can find in the description. Otherwise, thanks everyone for watching and listening. Don't forget to subscribe, and we'll see you in the next episode.